In this short video, we're going to show some important Excel etiquette for engineers, and I'll be using Excel version 2003. And to illustrate some of the basic Excel etiquette that should generally be used, I'm going to take the ideal gas law. Shown here is pressure times volume is equal to the number of moles times the gas constant times absolute temperature. And in this simple Excel sheet, we're going to set fixed values for the number of moles. Of course, the gas constant has to be specified with the correct units. We're going to assume a constant temperature, and then we're going to basically plot and see how the volume varies as a function of pressure. So we've got this constant and 1 over pressure. Very simple function. This applies to gas, of course, only, and really only at a limited range of pressures, but we're going to use the equation for a wide range of pressures just for illustrating some Excel techniques. And in addition to that, we're going to, in this little example, in addition to plotting gas volume versus pressure, we'll also plot the ratio of the gas volume at standard conditions divided by the volume of gas at some reservoir pressure and temperature. So VG is by definition at standard conditions 1 atmosphere and 15.56 degrees C or 60 degrees Fahrenheit. Now I'm using a version of Excel. It's 2003. It's because I haven't learned 2010 yet. And yes, I realize 2003 is about 10 years ago, and 2010 is only 2 years ago. Okay, I realize all that. I'm just a slow learner. But I think conceptually you'll catch most of the points that I'm making, and the difference between 2003. How many use 2003 still? How many use 2010 or 7? Okay, most of you. Okay. Well, it's my fault not staying up to date with technology that I can't show you all these things in 2010, because if I did that, you'd be hand-holding me. We'd never get anywhere. Okay? And I just want to get across some fundamental, what I call Excel etiquette. Excel etiquette for engineers. Okay? How you should do things and how you should not do things in Excel as an engineer. Okay. So we go in and we're just going to put something in here. Ideal gas law exercise. Okay. It kind of says what we're doing. It's me. There it is. Because your Excel sheets are not just for you. Your Excel sheets are for your colleagues and the people who remain behind you when you go to another company. Because you may be making Excel sheets that are used and will continue to be used after you get run over by a bus or you change companies. Okay? So they want to know who to blame. Okay? And then we've got, what is it, August 24th, 2012. Something like that. Basic stuff. What it's about, who's doing it, what's the date. Okay. And then I've got the ideal gas law. What I'm going to plot is on the x-axis pressure and on the y-axis volume. Okay. but I'll put it in like this, volume, and we've got units. I guess we can use, how many want me to use SI metric units? Okay, that's the majority. Sorry. Okay, I'll throw in a little of this field stuff. Okay, so we got cubic meters, except that's not very good. Bar absolute and cubic meters. Okay, we're going to do some stuff here. Okay, I generally center. Now, you have a trade-off in spending your time. And although m to the 3 is not clear that it's cubed, I know that 99 out of 100 engineers looking at my sheet will realize cubic meters. Okay? The one who doesn't, my time is too precious, because if I want to go in and do this as an exponent, format, cell, all this stuff, I have too much time. It means that I don't have enough kids yet, enough a wife, or or a life, a party. It's too much. But if you do this, you shouldn't be an engineer. Okay? This is totally, absolutely unacceptable, to put a number without a unit. And if you do it on your exercises when you hand them in, I'll ask the student assistants to hand it back and say it's not approved. Okay? You have to put units. Okay? So that's it. And do I write pressure or do I write P? Okay? That's a decision I have to make. It depends a little bit who it's for. Okay? It's a little bit up to you. I'm not going to dictate to you, oh, you have to write pressure and you have to write P. But in some situations, you'll find that you need to give enough explanation because you know the Excel sheet's going to be used by 3 or 4 other people. Then it's better to be clear, not to be ambiguous. So I got pressure and volume. I center these. And then I'm going to, the equation has temperature, and that's going to be fixed in my case here. I'm going to say, so what's the temperature? I have to give a unit, use C. We need the gas constant. This is SI units, which I should probably write, which is Pascal. It's actually, it depends how you want to do it. You can either use the 8314, which has Pascal, or I can go into that thing here, and I can say, oh, actually we have bar, this one here. I can use that. Bar, cubic meters, Kelvin, and kilogram. That's what I prefer doing. So I'll use, my units are bar. You don't really need absolute. Kelvin, kilogram, and what else? Cubic meter. Okay? And that number was 0.08314. 0.0831443. Okay? 0.0831443. Every number I input that I type in, every number in all of my Excel sheets, the last, I don't know, however long I've been doing, I put it in red. Now, why do I do that? Do I like red? It could be pink or it could be blue, or, okay. Why would I do that? It means that I can go back to an Excel sheet I wrote 6 years ago, and I can immediately identify on every sheet, in the file, what are the numbers I change? What are the numbers that I can change? All the other numbers will be calculated. And if you've ever worked with Excel, you'll find that that's one of the biggest problems. I hand you an Excel sheet, it's got hundreds or thousands or tens of thousands of numbers. You don't know which ones are being calculated, which ones are expected to be input. Okay? So every number I input, I just put it in red. Temperature. Pick a temperature. 100 degrees C. That's a good average reservoir temperature around the world. They range from 30C to 300C. But on average, or not 300C, but 200C. From 30C, shallow in Iraq, Oklahoma, to 200C, a few places. 200C is quite high. So I'll give you an average reservoir temperature, 100C. Got to make it red. Now I know that I have to use Kelvin in the ideal equation, right? Now I can either in the equation itself add 273.15, or I can do it once, okay? Instead of doing it in a bunch of equations. So what I'm going to do is I'm just going to calculate from this. I'm going to go up here, add the 273.15, okay? And then it's only done one place. And it's not in red because I don't want to change the Kelvin. It's calculated. Now the pressures of interest in petroleum are 1 atmosphere, which is about 1 bar, to about 1,000 bars. That's the range. More than 1,000 bars, it's probably out there somewhere. I haven't worked on it, and I've worked on most reservoirs around the world. So 1 to 1,000 bars, 3 orders of magnitude. So I'm going to do a range, and I want to plot how the volume in the troll field changes from 1 atmosphere or 1 bar up to higher pressures. Okay? And I'm going to put in here the volume of the troll field. Volume, I'll just write it as G. That's the initial gas in place. So it'll remind me. G is the symbol. And it was 45 10 to the 12th. Standard cubic feet. Okay? Okay. Now, because I want to make a plot of pressure from 1 to 1,000 bar, probably running out of time here soon. If I just write 1, 10, 100, 1,000, we'll have 4 points. It's not enough to get the kind of the number of points if I want to maybe do some smoothing or plot a line. So I probably want more than that number of points. But we got 3 orders of magnitude to go over, right? So how to do that? So this is generally how I do it. You can do like 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you do 10, 20, 30, 40, 50. Okay. Okay. So we can do that. Okay. And if you want to get clever, you can just do this. You can grab onto 2 of them and take it out until it gets 9. And then I'll do 10 and 20. And again, you can just grab onto that. We got 100, 200. And then 1,000. Okay? It's enough points. Now to calculate the volume, you need the pressure, temperature, and number of moles, right? Okay. We don't have the number of moles yet, right? But we do have of course now I'm mixing units. This is so instead of the 45 we could put in our number from the calculations here, though we have 2 numbers. 127.6. You like it better? You like the average? I'm not sure what to pick. 127.5. Let's take that. 127.5. 10 to the, what was it? 10th? Okay. Now we've got our metric. And now we're going to get kilogram moles by taking what? By taking this, well, we could just go over here and copy it from here, but we'll actually include that calculation in here. We take and divide the gas volume at surface conditions divided by our magic number of 23.6, I don't remember, 23.68. Okay. And that should not be in red. And by the way, since we put in these numbers here, the pressures at which we want to calculate the volumes, we input those numbers. I'll put those in red. And any questions about what I had done previously or am doing now? Okay. So, see the pressure times volume is equal to the number of moles, gas constant. And temperature, we want to calculate volume as a function of pressure. And we've got a constant, number of moles, a gas constant, and a temperature. So all of this becomes a constant. And then we're going to divide 1 over pressure here. Okay. So in this Excel sheet, we're going to put this equation in here. And that equation starts with an equal sign, as you know. And I'm going to group together these 3 numbers, which was the number of moles. And because it's a fixed address, when I copy that formula down to the next cell in row 14, I want it to be the same, B9. So I use F4, which is kind of the key to fix the address. You can cycle through with the F4 to make this a fixed address, either in column or row, or neither, or both, which is what we want here. And then times the gas constant, we'll just go up here to the gas constant. Again, we'll use the F4 to fix that address. And then we'll use the temperature up here. And I don't want to use 100 degrees C because in any of these equations of state, you're supposed to use absolute temperature. So we're going to use this one below in Kelvin. Again, locked to that cell. Okay, so that's the constant out front, and then we're going to divide by this, the absolute pressure. Okay, and we get some kind of volume there. And because it's a big number, it automatically takes this exponential format. And one of the things in engineering etiquette is that you generally, what you want to see in the way the number of digits is the number of digits your eye and your mind can process when you look at it. The computer has stored in it 15 to 16 digits. So don't worry about losing digits. It's there. If you want to look at it for some reason, 15 digits, you can get that. But all you want to try to make this as readable as possible so that when I look at things, I see only generally 3, at the most 4 significant digits. So I'll immediately crank this down to 3, okay? 1.67, you know what significant digits are. They're different than digits. And we got the exponent 12 there. Now we can copy this cell. If we copy this cell to the one below it, and what we'll see is that if we hit F2, we can make sure that it's doing what we think it should do. That's always a good idea. So you see it's got the fixed addresses to the number of moles, the gas constant, and the temperature. And then it's dividing now by 2 bar instead of 1 bar. Okay? You're going to write more complicated equations, and you're going to say, well, how should I check this? Okay? This is a trick that I often do. If I've already got one number that I think is being calculated right, and I'm copying that formula somewhere else, okay? Well, the problem is that now, in this new cell here, I've got 2 bar instead of 1, right? But if I put 1 here over here, kind of override the 2, I should get the same number. Okay? Now I can see the two numbers are the same, so I feel comfortable in that being correct. I can copy this down one by one. I can drag it down like that, but if it's a very long set of numbers, you get tired of dragging it down. So this is kind of a trick. If you've got this marked, this cell, and there's a column of numbers just to the left, that is the full length of what you want to copy down on, then you can just hit this lower right, double click that, and it will copy that cell to all of the cells below it until it finds the end of that column A. Okay, it's just kind of a trick. So I'm just going to do it like this, double click it, and you see that it fills it out down to there. Now if I would have had a blank column between A and the one I'm calculating, it wouldn't know how far to go down. I think it would go all the way down to 65,000 or something. So you have to have these two columns next to each other. So now we've got all these numbers here, and yeah, so that's the volume. Yeah. Okay, so this is the volume that this big gas reservoir would. Yes.
Would it do the same if we were working with rows instead of columns?
I don't think so. I'm not sure, but I don't think so. You can just try it. So this is the gas volume, this huge gas reservoir in the North Sea that has supposedly 1.28 10 to the 12 standard cubic meters. Now that means it's the gas taken up to this conditions like right around here, right? 15 degrees C and 1 atmosphere. About 1 bar. Now the question is, why is this not got a volume? If we take that gas in this table at 1 bar, why is the volume not equal to the 1.28? It's the same pressure, 1 atmosphere, I mean 1.0135, and 1 bar, that's about the same pressure. It's certainly not giving the difference between 1.67 and 1.28. Okay? Well, in the one case where we've got the initial gas in place, G, this is at standard pressure, 1 bar approximately, and standard temperature, which is 15 degrees C. Whereas this column of numbers here is being calculated at 100 degrees C. Okay? So you say, yeah, right, Curtis, expect me to believe that. So I can try to convince you by putting this to being 15.56, and we're getting a number a little bit closer to 1.28 there. Okay? Now, the troll field doesn't actually have a temperature of 100 degrees C. The troll field is shallower than that. I'm going to guess it's like, I don't know. You know, we could go look it up. I'd probably be wrong, but I'm going to guess 70 C. Does that sound like a good number? I don't know, 60 C. Do you think we can look it up or not? How many think we get it? If we look up troll temperature? I don't think we're going to find it. I'll just try it, just over the front of it. Troll reservoir temperature, North Sea. Huh? Do you see that 70 there? It looks suspicious, like I've done it before. Here it is. Sorry about that. Optimum temperature, that's probably not 71. Looks like 71. Fact pages. That's a cool site. That's a website we'll talk about later. That's the Norwegian Petroleum Directorate. There it is. It's got all sorts of cool stuff. I'll just search for temperature. There it is, 71 C. So I wasn't too far off. So we'll use 71 instead of, okay, so we're getting a little bit closer. Now what's the initial pressure? Because then we could find out how much reservoir volume is taking up. Okay? Reservoir volume is, need some kind of pressure. I'm not sure if it's got it here or not. That's too bad. I think it's around 2,300 psi. I'm just going to make a note of that. 2,300 divided by 14. This is one of those numbers that's going to disappear. Yeah, 158 looks right. So down here, I'm going to put 158 just to have one. I could do an insert here if I want. I could right click and insert and then put the 158 there. And I don't trust what it's doing without me telling it to do it, so I have to make sure that it looks like it's doing the formula right. So what it says is that the volume occupied down in the reservoir is about 10 to the 9th instead of this 1.28 10 to the 12th. Okay? And that ratio is the number that you'll be working a lot with as petroleum engineers. The ratio between that volume in the reservoir the gas contains and how much volume it would contain at standard conditions. And that ratio should be around, for most reservoirs, basically if you take it from the reservoir to the surface, it usually expands about a factor of 100 to 300, somewhere in that range. Okay? The gas expands somewhere around, let's say, on average 200 times, which means that, well, we can check that. We can take that number divided by, well, it'd be the other way around. Okay, is that number. So we got to go the inverse of that, which is 1 divided by that. And that's 130. So it's yeah. Okay. So it's expanding 130 times when it goes from the reservoir to the surface. Okay. That's a number we'll talk about later this week, probably. Okay. Any questions? So basically, we've got this volume, and I just wanted to show you how to do some plotting. Another thing we could do here, we could put, you know, we talked about two other quantities, little v, which is cubic meters per kilogram mole, right? Just to have some extra stuff going on. And we also have that z variable, which is equal to PV over RT, right? We could just make columns of those numbers. And to do that, we're going to just take the volume divided by what? The number of moles. But that's a fixed address, so we're going to hit that F4 and lock the number of moles in. So that's the molar volume. And again, I can just double click on that. It'll fill in all those numbers. There's not much difference between these two except just the number of moles. And then the Z factor is equal to pressure times little v divided by the gas constant fixed address divided by the temperature in absolute fixed address, bang. And that's a number, should have been 1, certainly at 1 atmosphere, because that's low pressure. Now here, you don't want exponential format, because the Z factor ranges from about 0.5 to 2 worldwide. Okay? It's not going to be less than 0.5, probably never less than 0.7, and it'll never probably be bigger than 2. The Kristen field in Norway, 900 bar, it's still less than 2. So we don't want exponential format. So I'm going to change the to a number. I'm going to give it 3 digits like that. I'm going to pop it down there like that. And lo and behold, we've got 1 everywhere, which is what we should have because we're using the ideal gas law. Okay, that's a good sign we haven't screwed up. Okay, so now we've got something we can plot. Save it once in a while because you know how the Windows craters. Yes?
You wouldn't expect to save it if you want to.
No. But we're using an equation that says Z is equal to 1 by definition.
Not because we're using a constant temperature?
No, it's because we're using this equation here because we're using that equation there. And Z is 1. Yeah, that's why we're getting z of 1, because,
Yeah.
you know, z, this correction term, is out here. Well, in the ideal equation, ideal gas equation, that is by definition 1. We'll come later in the next hour, we'll talk about the real gas law, and we'll see how it actually looks. Okay, so I'm going to plot, make a plot. I'm going to go through and make a plot. And to do that, I'm just going to mark the x and y. Okay, I'm going to have pressure on the x-axis, which is what I want, and volume on the y-axis. So I go in and I insert a chart. And you always, unless you become a manager, God forbid, paid lots of bucks, vice president, you know, something like that, you're going to use the XY scatter. You're not going to use line. You're not going to use any of these other ones unless you're a manager. If you're a real engineer, you use the XY. Okay? So if you turn it in your exercises during the class here using a line plot and they catch you, you will lose your firstborn. No, I'm just kidding. You will, it will not be approved as a, okay? So we're going to do that, and we're going to say next. And it's got some defaults that we're always going to change. We'll just go next. And I'm going to go ahead and put in the axis things just to get it over with. This is pressure in bar, absolute. And it's volume in cubic meters. I'm not going to make anything fancy with the... I'm going to put major grid lines. I'm going to always put major grid lines. Okay. And then I'll go next. And this is something, at least if you work with me, and if you turn in your exercises during the semester, you're always going to allow each chart to be its own sheet. I don't want to have your charts floating around in your worksheet. Okay? Why? So you always want to say, as a new sheet, you want to give it a name. We can just do something like this. This is volume as a function of pressure. It does allow parentheses. Okay? Why do you want it as its own sheet? The reason is that if it puts it inside this sheet here, it'll put it somewhere. But it may be, and you may decide to hide it from it, it may be way down here. Okay? Hiding. I don't know the figures down there, but I need to get to the figure. So I'm going to have to go to every one of your sheets knowing that you don't put the chart in its own sheet. And I'm going to say, well, he should have plotted this, or she should have plotted that. And I'm going to have to go looking around in all of your sheets, all over the landscape, looking for where you hit it. And I'm going to get real pissed off and not be a happy trooper. Okay? So every figure, if it's worth making, is worth giving it its own sheet. Okay? So there is a reason. It's not that I'm just maniac. Okay? So it's in its own sheet. And there it is. First thing you want to do. Bill Gates, when he had these people make Excel, owned printing. A lot of, you know how they make money on printers. You have to buy the cartridge, right? The cartridge replacements. Okay, so they make it gray in the back. So when you print this, it's using up all of your cartridge. Okay, and it's hurting the environment as well. So the first thing you want to do is you want to go to the format here, and you want to turn this area into white, the background into white, and you want to make this, the lines, black. White, black, and white. That's the first thing. You get rid of the gray background and you make the lines black. Okay? It takes you all of 2 seconds to do it. Then you click down here somewhere on the corner until the whole thing is marked, because Bill Gates also was selling microscopes. And in order to read those numbers, I have to have a magnifying glass or a microscope. They're so damn small. Okay? And if you copy this into a Word document, they become even smaller, and you're guaranteed that nobody can read your figure. Okay? So what we're going to do is the next thing is we click on the corner, and we go up and we change this either to 16 or 18. Doesn't matter, whatever you want to use, 16 or 18. All of the text becomes 16 now. Okay? Okay. Next, we've got too many. You don't need more digits on the axis than you need to read the numbers. So we've got 0, 2, 10 to the 11th, 4. We don't need those extra zeros. So we just kind of click on the numbers over here, and we make it like that. That's all the numbers we need, right? 1.4. You don't need this, right? It's just wasting. Okay, that's all you need. These are okay. Right now, we've got the legend out to the right here. I generally, myself, bring the legend inside here. This is not, you don't have to do that. I generally do this, but it's, okay. Because often these legends may get verbose, a little bit longer. And if it's out to the right, it'll make the chart itself get smaller and smaller. Okay, so that's... And then we want to go to the symbols here, which are very small, by default too small. I'm going to double click on them. Okay. And I'm going to make, this is what I learned when I went to school. It doesn't make it right or wrong. I'm going to make circles my default symbol. And I'm going to make it black on the thing around it and white like that. And in general, somewhere between 4 and 8 point, the size, between 4 and 8 point. If you have many points, then you tend to go towards the smaller point size. So 6 might be too much. We might try 5. If you only have a few points, you can use something like 8 to make them clear. You see them. Okay? Something like that. A little bit on the small side. I'm going to go up to 6. Something like that. Okay? And then if you want a line joining them, of course this is not a good plot because everything is kind of scrunched up around, the origin. So it's not a particularly good plot. So we're going to have to figure out if we absolutely want to have volume versus pressure, what can we do to make it useful for engineers? Well, there's a couple of things we can do. We can either make a plot of 1 over volume, which would be linear, okay? Because the equation is, if we plot 1 over volume, it's proportional with pressure. That would be a straight line. But you say, no, I want to see the volume. So what's our alternative? We want to be able to see some character to the volume. It's very hard to see anything here. So what might we do?
Change the scale.
Change the scale to what?
Negatives.
To
Change the scale to negatives.
to negatives?
Yeah.
But they're all positive numbers. Log? Use a log scale? Okay, let's try a log scale. Double click on the axis, go to scale, and use the logarithmic scale here. And when you do that, you can't have 0 or negative numbers, okay? You can't have 0 or negative numbers. So I'm not sure what we need, but it's not going to like, or maybe it'll find something. And the other thing with logarithms is that the major unit should be 10. And of course the minor has to be smaller than that. You can just use 10 on that too. But the important thing is that for log scale, you'll almost always use a major unit of 10. So go 10, 100, 1,000. Okay, so let's see. Okay, so now you see we only need to have numbers that are to 10 to the 9th. So we can go to 1E9 like that. Okay, so now we've got a little more character in our figure. It's a log scale from 10 to the 9th. You don't need that 0 there if you're going to use a log scale, right? We can add a line here. If you add lines, you always, with Excel, always want to use a solid line. And you want to use, in this case, it'll be black, and you want to use the largest one in general. Okay? And then there's an option here, smooth or not. If it's a smooth function, you can use the smoothing. If the points are like, scattered around, you don't want to use the smooth function. So in this case, it's pretty smooth, so we can do something like that. And you see you got a pretty nice plot. In fact, I'm going to even kick this up closer to 8. So you see the points, you see the line. You see the line doesn't go through the points because I chose white for the center. And this is almost ready to send home to Mom. It's a nice figure. Okay. Now there is a lot of stuff going on. You see there's a lot of change in volume here and a very small change in pressure, right? So it's not particularly good engineering plot because a lot of stuff's going on, but I can't really differentiate. I can with the computer. I can just put my cursor on it, but I can't do that if it's printed, right? So it's almost, these data here are almost useless if it's printed. So I say, well, I want to do something about that. I'm going to use a log scale on the x-axis also, because it goes from 1 to 100. So I'll do a log scale on that. Again, we know we have to use the major as 10, and that has to be smaller. And we don't want it going from that. And we know the largest pressure we had in our table was 1,000, right? Bar. That's looking good. Okay. So now we've got a log-log plot of a linear function, which is a straight line. And the slope of this is exactly 1, of course. Okay. Okay. I'm going to leave this here for the time being. We've got volume, we can read it. We've got a nice log-log scale. If you want to add some tick marks, you might do that. That's under the chart options, grid lines, minor grid. It helps in reading log scales because it's not intuitive. So you might add something like that. And now you can actually read this as 20 bar. You see, you wouldn't have thought that was 20 bar, and you certainly wouldn't have thought that was maybe 90, but because it's not a linear scale. So this for log-log is often common to put the minor as well as the major grid. Okay, that's a pretty nice plot. Okay. Let's see, was there anything else about plots that I wanted to comment on? No. Okay, so I'm gonna make one more plot just to kind of go through this again. Now, this time I'm going to plot 1 over pressure. I'm sorry, not 1 over pressure. 1 over volume. I'm going to plot 1 over volume. Okay, so that's going to be text. So 1 that, and that'll be 1 over cubic meters or something like that. Is that okay? And by the way, we probably, it would have been safest to write VG because it's an ideal. We're using the ideal gas law, so these are gas volumes. So I'm going to go ahead and put G there. The Z factor is normally used only for the gas, but we can go ahead and write it like that, and then I'll just add the G onto here. Okay. By the way, if this gets a little bit where you can't read it, if the column's too narrow, you just double click on that line between the 2 letters and it'll find exact width it needs for C. Okay. Now it's saying it needs that for this thing here. We don't really need that. We can make it a little bit smaller, something like that. Okay. So now I'm going to plot 1 over V. And to make it a little more interesting, what I'm going to do is I'm going to plot. What I'm going to plot is this initial surface gas volume divided by V to make it a little bit more interesting, because that actually means something. So let's do it this way. We're going to plot G, the initial gas in place, divided by VG. Okay. So that's, you don't know Y yet. That's a fixed address divided by the volume, like that. We double click on that corner. We don't need exponential format for this. I don't know why it keeps coming back. We'll just use a number, something like that. Okay. There's our 130 number. That's how much it expanded, right? Okay. So this number kind of represents the expansion of the gas going to surface conditions. Okay? We'll call that something later. I'll just call it gas expansion. So maybe I want to put a little bit of text in this case. So I do this. I'm going to call it the gas expansion to standard conditions. Okay? So that's just kind of a little bit extra text there. And now I'm going to plot that. So to plot that, this is kind of a pain. I've got to mark the x-axis first. Okay, and then I can hold down the control key and mark the y-axis. That. Insert, chart, XY scatter. I'm not going to do anything there. I'm going to put the major axis. I'm going to put the titles on there. This is, again, pressure. And this is going to be our gas expansion, G over VG. Okay? And the units of that would be standard cubic meters per cubic meter. I mean, those cubic meters cancel, but it's often in petroleum engineering useful and necessary to include them, cubic meter per cubic meter. Okay? So we'll do that, and then next we're going to put it as its own sheet, and I'll just say gas expansion as a function of pressure. Okay. Okay, Bill, we're not going to let you take our money. We're going to make that white. We're going to save the environment. Thank you. We're going to grab onto the corner, make it 16 point. We're going to get rid of the unnecessary digits on the y-axis. Because I'm neurotic, I'm going to move this over here. It's not really SY because we're going to make those symbols bigger. Circles, black, white, line, big, black. Okay? Smooth, fine. There we are. Nice figure. Okay? Yes?
Just in the previous spreadsheet, the very first point, yeah, that one, when it's 1 bar A, I would have thought that would be closest to 1.
Okay, it's because
They're both at atmospheric pressure.
that's exactly right. So let's take a look at that. So the gas volume at 1 atmosphere, or 1 bar, and I'm sorry, 1 bar absolute, and T standard conditions divided by the volume of gas at 1 bar atmosphere and reservoir temperature, right? That's what we're doing. Okay, the number of moles is the same, the gas constant's the same, so we can write those two out. We got N, R, T standard conditions, or N, R, T reservoir conditions. The pressure would be pressure at, well, in this case it's whatever, it's 1 atmosphere. And these are going to cancel, of course. Those cancel, and we're left with this ratio.
You also need to include like 1.013
Okay, well, that's, yeah, I'm approximating. This would have been, this is actually 1.0135. Okay, so that would be 1.0135, and that would be 1.0 from our table.
Yeah.
But that's not giving us the big difference.
Yeah.
No, it's this ratio of temperatures. So that's whatever's 273 plus 15 divided by, yeah. So that it's coming from the temperature ratio.
Okay, thank you.
Okay, that's 0.8 approximately. Any other questions? There's no bad questions unless I can't answer it. No, just joking. That's the only joke you're going to get today. So. Okay. All right. So we got two pretty nice figures. You can certainly send it home to mom. You can put it in a publication. You can put this in a report. You can copy and paste it into Excel, into Word, or PowerPoint. You got to do nothing more. What most of you engineers will be doing, unfortunately, you won't take that extra 1 minute to do the Curtis, Excel engineering etiquette, to clean it up. The 1 minute it takes, or less, to clean it up, every figure you make. And what will happen is that the boss will say, we have a meeting tomorrow and I want you to get this presentation ready and I want your figures to look professional. And you're just going to say, oh shit. You're going to have to call home to your spouse and your kids and tell them you're not coming home. Okay? And you're going to be cleaning up all your figures that you didn't take time to clean up then and there. Okay? So just do it. And if a figure is not worth fixing up like that, the 30 seconds it takes me, 22, okay? 22 seconds. If it's not worth that, it's not worth making a figure. The figure is the greatest engineering tool. So when you make them, you do it for a reason. And you have usually a good reason. So do it, but clean it up. There's nothing more you got to do with these figures. And you saw how short a time it took. Plus the fact that you're not going to pass the exercises and go up to the exam unless you do this, okay? So at least this semester you'll be doing it, okay? Any questions about the Excel stuff we've done? So, simple table. Now, I'm not going to go through all this, but I've tried to summarize all this stuff into just some comments here on the figures as well. That'll be part of the written material. I'm not going to go through it. Okay? Now, what I've decided to do is ask one of the PhD students at the Institute who knows 2010 Excel to do this same exercise and record it. We actually may bring him in here and he'll do it and then I'll kind of narrate it while he's doing it. So I'll be learning how to do it in Excel 2010. And then we'll get you a video of that as well. And because I realize most of you don't use the 2003. To me, it seems more difficult to do these things in 2010 than in 2003. But I'm probably wrong. We'll see when he comes. He's supposed to be an expert. Okay? No questions or nothing? Yeah.
In that gas expansion plot, as the number gets larger, the volume of the gas actually decreases. Is that right?
Yeah.
So
Yeah, because if you start at 1 atmosphere and 70 degrees C, and all you do is cool it, then you're changing the volume by 20% from. That's all you're doing.
I mean, by the name of that gas expansion, I get the feeling that as the number gets larger, it must, volume must, increase.
Well, what it's saying is that if you had the same Troll reservoir, okay, but at an initial pressure of 1,000 bar, which they actually have reservoirs in Norway close to that, just put the same amount of gas in a reservoir, 10,000 meters deeper or something, okay, very deep, and it was 1,000 bar pressure, okay, then you would need a much smaller volume to contain that same amount of gas, okay? You would need, in fact, somewhere, I don't remember, maybe a factor of 4 smaller volume. So the ratio of getting this 45 10 to the 12 standard cubic feet of gas, you'd still get that same amount of gas, but from 1/4 of the volume. So the expansion would be 800 times instead of 130 times. Instead of 130 times, it would be 800 times. So the expansion from 1,000 bar to atmospheric pressure is 800 times expansion. Whereas down from a low pressure, it's only, like Troll, it's 132 times the expansion. Okay, we'll take a break.